morning. Good morning. It's 4:30. Just doing my morning work, and I wanted to share a question here. So, a friend Napoleon from winter 2021. Napoleon, I see your question. You said, "Hey, I would prefer if you call me Jeff, but okay, that's cool. Hey, Professor Anderson, at 1 minute and 40 seconds into this video, you multiply matrices B, C, and D inverse in that order. Could you explain why it matters? What outputs could we expect if we multiply in the other orders?" So this problem, kind of give you an answer to this problem. I kind of forget at the moment. So what we're going to do is develop this problem. I forget the way that this problem started. Let's take a look. Yeah, so we can actually write that down. Let's capture that matrix. And we'll try to get an answer to your question, Napoleon. So here we go. So we're going to let the matrix A be that matrix that we saw on screen. It's a 4 by 4. Just move this over a little bit. It's going to be 5, -10, -5, 10. Not the best rows I've ever done. 2, -7, -11, 16, 3, -5, 1, 0. And then we've got 6, -10, 4, -2. And then instead of answering your question using that stupid TI calculator, I mean, I like the TI calculators as reminders of the days gone past, but I don't like it from the standpoint that it's not very sophisticated compared to what we got online. So what I'm going to do, Napoleon, is actually answer your question with a proper notation and also using a much more sophisticated calculator, which is Octave Online. And if you remember, we actually use Octave Online in lesson 17 or 18. I kind of forget at this moment. Let's see, I need a new tab. There we go. So we're going to go over here and put Octave. And then we're going to go to the online version. And at some point, I'm going to actually get serious and create my own account and kind of have fun with this, but I don't need that right now. And I also, at some point, I'm going to support this with a little bit of money because I know how much energy it takes to make this type of stuff. I do it nonstop. Okay, so let's go ahead and store that matrix in Octave Online. So what we're going to do is actually just type in the values. This is going to be 5, 2, 3, 6. And that's row 1. And then we're going to get -10, -7. Commas demark columns. -10. Next row. -5, -11, 1, 4. And then we'll go down to the next row and we'll say it's 10, 16, 0, -2. Okay, I'm going to go ahead and check that that matrix matches the one that I'm trying to do analysis on. So we've got 5, 2, 3, 6, -10, -7, -5, -10, -5, -11, 1, 4, 10, 16, 0, 2. Okay. So now what we're going to do is start to do Gaussian elimination on that. And remember, Gaussian elimination, to do those rows, we're going to take the non-pivot divided by the pivot with a negative on that division. So we'll start with L1, and we're going to define L1 to be the 4 by 4 identity matrix. So this command I44 means the 4 by 4 identity matrix for what we see here. And then I'm going to go ahead and define entry 2, 1 is going to be -10 divided by 5 with a negative. So -10 divided by 5. So notice that gives me this entry. And then we're going to say L1 of 3 comma 1 is going to be negative, and we'll take the subdiagonal element in row 1. So this is going to be negative 5 divided by the pivot element, which is 5. And then I'm going to go ahead and just do the last one as well, because I don't need 2 different lines of code to do that. So this is going to be negative subdiagonal element 10 divided by the pivot. And I'll go ahead and push enter. Okay, so now if I do L1 times A, I get that matrix. So that gives me L2. I'm going to call this I4, comma 4. L2 of, I'm going to take the subdiagonal element. So this is going to be 3 comma 2. And that's going to be negative non-pivot divided by pivot. And we'll do the same thing, L2 of 4 comma 2, sugar. So 4 comma 2. And that's going to be equal to, go ahead, let's see. So that's going to be negative 12 divided by negative 3. Okay, so now we do L2 times L1 times A, and that should give me that one. And then we'll go L3 is going to be I of 4 comma 4, and then we'll take the 4th entry in the 3rd row, and we'll say that that is going to be negative of the subdiagonal minus the pivot. So negative 2 divided by 1. So now I got, if I push up, that will get me back to this one. And now I have L3. Okay, so now we've set up that. Let's go back to our analysis here. I'm still figuring out my contrast balance. It's such a frustrating experience. Okay, so what we've just done here is we've seen that L3, in the way that we've just defined it, times L2 times L1 times A is equal to my upper triangular matrix U. So let's go ahead and turn this off. Buddy, Art is going to help me with this. There we go. Contrast balance is a little better there. So this U is the upper triangular matrix that I have there. And then what we're going to do is we're going to peel these off to bring all of those L's over to the other side. So the first thing that we do is we multiply this by L3 inverse. So because the idea is that I want to get this over here. So if I multiply the left-hand side by L3 inverse, I've got to also multiply the right-hand side by L3 inverse. Well, it just so happens that L3 inverse times L3, that's going to be the 4 by 4 identity matrix, because each of those is a 4 by 4. And then the identity matrix times L2 is just going to be L2. So now we've got L2 times L1 times A equals L3 inverse times U. But then we're literally going to do the exact same thing. We're going to peel this one off. So to peel that one off, we're going to go ahead and multiply by the inverse times A. But if I multiply this side by the inverse, anything I do to the left-hand side, I must also do to the right-hand side. So that is, okay. So these two things go away because that's the n by n identity matrix. And then now I'm left with the statement that I've got L1 times A equal L2 inverse times L3 inverse times U. And then this is, of course, where I'm going to peel off the last one. But if I peel off the last one, those two things go away. And now I get A equals L1 inverse times L2 inverse times L3 inverse times U. And then the claim here is that this means that this is L times U, where L is the product of those matrices. And this is where things get crazy, because if I look at L1, and then if I take the inverse of L1, notice that the only thing that's changing is the signs of those. So specifically, if I look at inverse, so we got to kind of be crafty here. L is going to be L1 inverse, L2 inverse, L3 inverse. And specifically, it's going to be the inverse. So we'll say L is equal to inverse L1 times inverse L2 times inverse L3. And that's that matrix that we have in that order. And it ends up that these are just the negatives of the Gauss transform lower triangular piece, right? So let's look at column 3. Here's the Gauss transform, and this is the negative. Here's column 1. That's the Gauss transform. Here we just have the negative. Now, your question, Napoleon, was what happens if we do it in the opposite order? So specifically, let's define this new variable called not L, and we'll do it like this. And this is where we get cross-pollination. Notice that's not the same matrix. And in fact, when we put L times U minus A, oh, sorry. It's complaining because I haven't defined U yet. Let's try that again. That's not 0. If they were the same, if this matrix times U was A, then this would be 0. But this thing is definitely not 0. In other words, when I'm looking at this matrix and I've done it in the opposite order, I do not get the L that I want. So I think somewhere in these playlists, actually, to be honest with you, we actually go deep into the reasons why this is true. I don't really remember where that is at the moment. Let's take a look. So I hope that answered your question, Napoleon. Please do watch this video and then respond back to that comment that you left. But somewhere in the proofs, I definitely know that it's on our review, inverting Gauss transforms for LU. I think we do it there. And then proof of inverse of Gauss transforms. I think this is a really nice one. Yeah, let's see if this one's it. Yeah, so this gives us, this video actually gives us how we can think about what the inverse of the Gauss transform is. And then I believe somewhere on this, this playlist, or even in the tests, it may be that the case, it's somewhere in these tests, it could be. I don't remember exactly where it is. Maybe one of our other viewers can help us with that, where we can find the answer to why this works out in the way that it does so beautifully, and the other one doesn't work out. But the short answer to your question is the reason that it's in this order is because we're peeling off the lower triangular matrices, starting with the leftmost matrix, which means L3 goes first, the inverse, then L2, then L1. So hopefully that helped. Thank you so much for your question, Napoleon. All right, I'm going to see this. I'm testing this for the first time, being able to answer questions via video. So I'll go ahead and link this for you. All right, bye.